So today I want to help you make sense of variables without any theoretical input. An exploratory factor analysis, or EFA, is a powerful statistical technique that's used in the psychological, sociological, educational sciences, and even market research. And it helps us identify the underlying factors or the constructs that we use in a large set of observed variables or indicators. The ultimate goal of EFA is to reveal the latent structure of the data, and that is to identify underlying dimensions or factors that explain patterns of relationships among these variables. When a research study is initiated with no explicit theoretical framework to guide the examination of relationships among a set of variables, EFA is often the go-to approach. It serves as an exploratory step in data analysis, and this provides invaluable insights into the underlying structure of the data. In these cases, EFA acts as a stepping stone, and it helps researchers generate hypotheses or even develop new theoretical frameworks based on the observed patterns in the data. However, it's important to understand that the strength of EFA is also its potential weakness. This statistical technique operates without any prior theoretical input by design, as it's meant to explore the data without the influence of preconceived theories. This freedom allows for an unbiased exploration of the data, and this reveals latent variables or dimensions that may not be immediately obvious. Nevertheless, the absence of theory can also be seen as a weakness. Without a guiding theoretical framework, EFA can sometimes yield ambiguous or even unreliable factor solutions. Now, in this vein, an important adage that's often quoted in the context of EFA is, it's not the data's job to tell you what you're measuring. And this statement emphasizes that while EFA can help identify underlying factors, it does not attribute conceptual meaning to these factors. In other words, EFA is like a tool that can uncover patterns in the data, but interpreting and labeling the factors that emerge is entirely up to the researcher. I want you to consider an example where EFA is employed in a study examining symptoms of depression. Suppose the study involves a large data set with various self-report measures related to depression symptoms, such as mood, sleep, appetite, and loss of interest. By conducting an EFA on these measures, the analysis might identify several underlying factors. It's then up to the researcher to interpret and name these factors, which could represent aspects like emotional distress, sleep disturbance, appetite changes, and anhedonia, which is the loss of interest or pleasure. Now, the researcher would examine the factor loadings of the depression symptoms on each factor to determine their relevance and strength of association. Understanding and conducting exploratory factor analysis involves several key steps and considerations. And this includes knowing when to use EFA in research. Also, you need to understand its underlying assumptions. And you also need to be familiar with the different methods of factor extraction and rotation. While EFA can be helpful in reducing the number of variables and identifying underlying factors, it's crucial to approach the interpretation of results with caution. The lack of theoretical input in EFA means that researchers must exercise their judgment and rely on existing knowledge to make sense of the factors that emerge. Additionally, factors should be interpreted and labeled based on their relationships with the observed variables and guided by theoretical consideration. There's different starting assumptions and different mathematical approaches when you're looking at a common factor model versus what's called a components model. Now, at its core for EFA, it's a question of what is the causal agent, the latent construct or the observed variables? Are we explaining or simply reducing? There's principal components analysis, which is another frequently used technique for data reduction in psychological research. Now, both EFA and PCA both serve to simplify complex data sets. They both also operate under different underlying assumptions and goals. PCA doesn't care what the components are or if they're interpretable. EFA does. Now, EFA's main objective is to uncover the latent constructs or the factors that account for the patterns seen in observed variables. Its focus is not merely on data reduction, but on identifying and interpreting underlying structures within the data. This approach often aligns with theoretical considerations, striving to discover meaningful and interpretable factors that resonate with prior knowledge or theoretical frameworks. Furthermore, EFA assumes what's called a causality principle, and this posits that latent constructs, also known as the factors, are responsible for the variations seen in the observed variables. Now, from a mathematical standpoint, EFA models are designed with unique error terms for each observed variable. This design allows for the estimation of measurement error and provides specific factor loadings for each variable. Consequently, though, EFA aims not to just simplify, but to explain the observed variable's variation by identifying the underlying factors and delineating the relationships between these factors and the variables. Now, in contrast, PCA's primary concern is reducing the dimensionality of the data by capturing as much variation as possible within a smaller number of components. It does not explicitly consider latent constructs, but seeks to identify linear combinations of the observed variables that account for the maximum amount of variance. Now, as such, PCA is less concerned with the theoretical interpretation and can sometimes generate components that, while mathematically derived, might lack clear conceptual meaning. Unlike EFA, PCA does not propose any causal relationship between the components and the observed variables. It treats all observed variables as equally important and is solely focused on variance maximization. The primary question PCA answers is not one of explanation, but of reduction. Its central goal, again, is to reduce the data's complexity, irrespective of the interpretability or explanatory power of the resulting components. Now, while both are used for data reduction, they both represent different perspectives. EFA is oriented towards uncovering and interpreting underlying latent constructs and assumes a causal relationship between factors and observed variables. PCA is primarily focused on reducing data dimensionality and capturing maximum variance, without a specific emphasis on latent constructs or causal relationships. Now, hence, the choice between EFA and PCA should be guided by your research question and theoretical considerations and the overall goals of the analysis. Now, quick summary, PCA assumes that all variance in an observed variable is usable and should be considered. PCA creates components based on the total variance, and that's both common and unique in your data set, while EFA creates factors based on the common variance only. And we're going to see a Venn diagram that illustrates both of these concepts. PCA would be most appropriate for reducing the dimensionality of a large set of variables and is typically used when the goal of dimension reduction and to visualize your data. PCA would be most appropriate for creating a smaller set of uncorrelated variables that still capture the most important information. EFA makes more assumptions about the structure of the data. For example, that there are latent factors influencing the observed variables, and that's different than PCA. EFA aims to identify the minimal number of factors that can account for the common variance, which is correlation between a set of variables. EFA is more appropriate if the main objective is to uncover the underlying structure of your observed variables without any preconceived notions of how many factors there might be or which variables load on which factors. And I want to give you some scenarios. In this first scenario, a psychologist is conducting a study on stress in clinician training. They've collected data on 50 different variables, and they want to understand how these variables group together to represent different aspects of workplace stress as a clinician. So which method should they use? Pause the video here and think about which method would they use. Okay, so here, EFA would be the most appropriate to understand how variables group together to represent different aspects of clinician workplace stress. Also, EFA would be appropriate because the researchers interested in uncovering latent factors that influence the observed variables, and that would be the different aspects of workplace stress. Now, I have some examples for my future neuropsychologists in this class. A team of neuroscientists have conducted an experiment where they've collected data from 200 different locations in the brain while subjects were performing a specific task. The data results in a large amount of variables, and they're interested in visualizing the major patterns in their data and reducing its dimensionality for further analysis. Which method should they use? Pause the video now and think about this question. Okay, so here, PCA would be the most appropriate method. It would help in reducing the dimensionality of the data and summarizing the major patterns in a way that can be easily visualized and interpreted. In this scenario, the neuroscientists primarily want to reduce the dimensionality of their data and identify the major patterns. This is a task that principal components analysis is particularly well suited for. PCA, again, is a technique that identifies the directions, i.e., the principal components, in which the data varies the most, without assuming any underlying latent structure or constructs. Also, PCA is the best choice as it does not assume any underlying latent structure. On the other hand, let's say we would use EFA for this scenario. When would it change? Well, EFA would be useful in this scenario if we're interested in understanding the underlying latent variables or the factors that give rise to the observed data, because EFA assumes that the variables are related to each other because they're influenced by this common unseen factors. If the neuroscientists were specifically interested in identifying latent factors or constructs that were causing the observed patterns of brain activity, then and only then would EFA be more appropriate. However, given the scenario description, PCA seems to be a better fit for the goals of the neuroscientists. The scenario here would lean more towards EFA if the neuroscientists were not just interested in reducing the complexity of their data, but specifically in understanding the underlying latent constructs that might be influencing the observed patterns of brain activity. For instance, if the neuroscientists had a theory that certain patterns of brain activity might be influenced by several unseen factors like stress levels, sleep quality, and cognitive load, they might use EFA to test these ideas. The goal here would be to uncover whether these theorized constructs can be identified as factors in their data, and if so, which observed variables relate to which factors. And in EFA, they would be aiming to explain correlations between the observed variables with a smaller number of unobserved latent factors. So if the statement read, neuroscientists have gathered a lot of data regarding different patterns of brain activity, they suspect that the observed variables might be influenced by several unseen or latent variables. They want to uncover these latent variables and understand how they relate to the observed variables. That would be when EFA would be more appropriate. And lastly, I want to give some examples of PCA and EFA for my forensic psychologist folks. So let's say some forensic psychologists are working with a large data set from prisoner behavior assessments. They've collected data on hundreds of variables over several years, including age, offense history, drug use, educational background, family history, mental health diagnoses, behavior within prison, etc. Their primary aim is to reduce the complexity of the data and highlight the most important variables that contribute to prisoner behavior. They want a smaller set of new variables, which can be a combination of old ones that capture as much of the variance in the data as possible. So, should they use PCA or EFA? Pause the video now and think about this and why. Now, in this case, PCA would be the appropriate method because the goal here is to simplify the data set by identifying a few key components that can explain the majority of the variance in the data. Now, a separate scenario, let's say these forensic psychologists are conducting a study on the underlying psychological traits that might contribute to criminal behavior. They've developed a new questionnaire consisting of 100 items that respondents rate on a 7-point scale. The questions touch on a wide range of topics from personal history, social behavior, emotions, morality, and so on. The psychologists believe that these items that respondents rate might group together in a way that reveals several underlying unseen psychological traits. They want to explore the structure of these questions to uncover these latent traits. So, should they use PCA or EFA? In this example, it's going to be the opposite of the previous one. So we know EFA would be the most appropriate method, but why? Well, the goal is not simply to reduce the data, but to explore potential latent variables or factors. In this case, psychological traits. And this would be to see, do these psychological traits influence the responses? The psychologist in this scenario would believe that these traits, which influence the questionnaire responses, could be grouped to reveal underlying patterns. The latent cause model and the composite prediction model represent two different ways of understanding the relationships between latent variables and observed variables. The latent variables are your unobserved or hidden variables, and your observed variables are your measurable variables or your manifest variables, also known as your indicators. Now, in the latent cause model, which is our common factor model, this is a model where an invisible or hidden trait causes visible behaviors or results. In this model, the latent variable is seen as the source, and the observed variables are the outcomes. It's kind of like the root of a tree that causes the branches and leaves to grow. The root of the tree would be the latent variable, and that would cause the branches and leaves, which are our indicators, to grow. In this example, therapist quality is the hidden trait that influences or causes the observed qualities of listening, diverse skill sets, and warmness, which you could also think of as a therapist's overall quality is seen as the root cause that leads them to be good at listening, have diverse skill sets, and exhibit warmness. On the flip side, the composite prediction model looks at the observable behaviors or results and uses them to estimate or predict the invisible trait. Now, in this model, the latent variable is seen as the summary or the outcome, and the observed variables are the inputs or causes. It's like taking the size, shape, and color of the leaves, which would be your observed variables, to guess the type of tree, the latent variable. Let me repeat that. It's like taking the size, shape, and color of leaves to guess the type of tree, which means that it's like taking the observed variables to guess the type of latent variable. Now, in this example, that means listening, diverse skill sets, and warmness are used to predict or estimate therapist quality. In other words, by measuring a therapist's listening ability, their range of skill sets, and their level of warmth, we can get an idea of their overall quality as a therapist. So while the latent cause model, which again is our common factor model, perceives the latent variable as the cause of the observed variable, our composite prediction model considers the latent variable as the summary or a composite score of the observed variables. Keep in mind, the composite prediction model is also referred to as the component model. Let's break down each component of variance in a common factor model and then visualize it as if we were describing a Venn diagram. I want you to keep in mind that you'll never see a Venn diagram in the literature represented this way. This is for learning purposes so that you kind of get an idea of what does it mean to look at a latent variable and the three indicators in this specific example. In a common factor model, we have three main sources of variance. We have common variance, we have unique variance, and error variance. Let's talk about common variance first. This is the portion of the variance that's shared among the observed variables due to one or more common factors. And in our Venn diagram, imagine the three circles representing y sub 1, y sub 2, and y sub 3, which are the observed variables, and they intersect. Well, that intersection is the area in which that circle overlaps with one another. That is the common variance. This common area signifies the shared influence of the latent factor on all three variables. And here it's represented by this pink center spot right there. We also have unique variance, and this is the variance that is unique to each observed variable, and it's not shared with others. And in the Venn diagram, it would be represented by the area of the circles y sub 1, y sub 2, and y sub 3 that do not overlap with the other circles. Each of these areas indicates the unique influence that the latent variable has on a particular observed variable. So let me draw this out. This is our unique variance for y sub 1. This is also our unique variance of y sub 2. And this is also our unique variance of y sub 3. Now, we also have the error variance. And this is the variance that is due to measurement error or other unexplained influences. And in the Venn diagram, you could think of it as being visualized as a separate circle for each observed variable, y sub 1, y sub 2, y sub 3. That's not overlapping with the other circles, kind of like the unique variance, except we don't see it here because it's the areas that are unexplained in each observed variable that's not accounted for by the latent factor. So it is related to unique variance, but error variance specifically is looking at the variance that we cannot see, hence why you don't see it in the Venn diagram. But then I also want you to consider this concept called local dependence. That is a new term for saying covariance, which we all have heard of before. Now, by definition, you cannot take a covariance of more than two variables at once. For instance, we can't have the covariance of y sub 1, y sub 2, and y sub 3. You have to find the covariance of a pair of variables at a time, which means that if we have three indicators, then we have three local dependencies. And that would be right here. For y sub 1, y sub 3, for y sub 1, y sub 2, that'll be this area, including the pink part. And for the last one, for y sub 2, y sub 3, that'll be just this shared area all in the middle. That is the covariance. It's the degree to which two observed variables, meaning one of our circles, are related due to the influence of the latent variable. And in the Venn diagram, again, this is the area that's represented by the overlap of the two circles, but not including the area of the common variance with the third circle. Lastly, the total variance in an observed variable is the sum of these three types of variance: your common, your unique, and your error. In the Venn diagram, this would be represented by the entire area of a given circle, which includes both the overlapping areas, which represents the common variance and covariance with other variables, and the non-overlapping area, meaning the unique variance and the error variance. So when I say total variance of y sub 1, I'm just talking about the entire circle. If I want the total variance of y sub 2, I just want this entire circle. And lastly, if I want the total variance for y sub 3, I just want this circle. I also want to give you a scenario to kind of clarify the idea of covariance. It is not equal to the number of indicators in your model. And I'll illustrate that real quick. Imagine that this latent variable now predicts 5 indicators, each one with its own unique error variance. This would mean we now have y sub 1, y sub 2, y sub 3, just like we did in this example, which, if you remember, we took this covariance, and this covariance. That is why we had 3 different local dependencies. But again, does not necessarily mean they equal the number of indicators you have. And I'll prove that right now with drawing 5 indicators. We now need to find the covariance of y sub 1 and y sub 4 and y sub 1, y sub 5. Moreover, we need to look at the covariance between y sub 2 and y sub 4 and y sub 2 and y sub 5. Then we need to do this for 3, y sub 3, y sub 4, and y sub 3, y sub 5. But don't forget, last one, the last pair at the end, which is y sub 4 and y sub 5. This leaves us with 1, 2, 3, 4 for the first set, 5, 6, 7 for the second set, 8, 9, and 10. So here, if you had 5 observed variables, you would need to calculate 10 local dependencies, i.e. 10 covariances. Now, when I'm talking about this, imagine you're drawing 2 more circles here somewhere. This may or may not be on an exam, so rewatch this part. The conditional independence model. Here, therapist quality is a latent variable that influences 3 observed variables: listening, diverse skill sets, and warmness. The small e represents the error term, or our unique variance that's associated with each observed variable. This model assumes conditional independence, which is a fundamental concept in SEM and factor analysis. Conditional independence implies that once we account for the latent variable, therapist quality, the residuals, or the unique parts of the observed variables, are independent of each other. In other words, any correlation or covariance between the observed variables can be fully explained by their common relationship with the latent variable. After accounting for this shared variance, the remaining parts of the observed variables, which are the parts that are unique to each, are assumed to have no correlation with each other, which means mathematically the covariance is equal to 0. This assumption greatly simplifies our model. It implies that all relationships between the observed variables go through the latent factor. This is quite different from the scenario we discussed with the Venn diagram earlier, where there could be local dependencies or direct covariances between pairs of observed variables. Here, we're assuming those local dependencies do not exist. However, this assumption doesn't always hold in practice. In some cases, there might be residual correlations between observed variables that cannot be fully explained by the latent variable. This might also be due to measurement error, secondary latent variables, or other factors. And in such cases, we might use confirmatory factor analysis to modify our model, which is the topic of another lecture. In this diagram, therapist quality is a latent variable, and it's hypothesized to reflect of listening, skill sets, and warmness. The observed variables are also known as indicators. Quick summary. That being said, an indicator score is equal to the loading times the factor score plus the error, which is what you're seeing in the middle between those two diagrams, which is x is equal to a times f plus e. It's just like regression. Factor loadings, the a's, are the same thing as the regression coefficients, your b's. Observed indicators are your dependent variables, and your latent variables are your predictors. Each path from the latent variable to an observed variable is labeled a sub 1, a sub 2, and a sub 3 respectively, and these labels denote the factor loadings, which are basically, as I said, regression-like coefficients that measure the strength and direction of the relationship between the latent variable and each observed variable. Each observed variable also has an error term associated with it, and that's represented by E. These error terms represent unique variances, or the portion of each observed variable that is not explained by the latent variable. These might include, again, measurement errors or influences from other unmodeled variables. Once again, the equations listed, x1 is equal to a1 times f plus e1 dot 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 all the way to x3 equals a3 times f plus e sub 3. These are mathematical representations of the relationships that we see in this diagram. X stands for your observed variable score, a is the factor loading, f is the factor, which is, by the way, as a reminder, the latent variable, and e is the error term. So in this model, each indicator is a linear combination of the factor score and the error term. Once again, as a reminder, this is a regression-like equation with factor loadings playing the role of regression coefficients. The observed indicators are the dependent variables, like in regression, while the latent variables are your predictors. And factor loadings, which we'll expand more in a couple slides, they tell us how much the observed variable is expected to change for a 1 unit change in the latent variable, assuming all other variables are held constant. I want to unpack this concept of leftover variance that's not explained by a common factor. In factor analysis, each observed variable or indicator, if you remember, is thought to be influenced by one or more common factors and a unique factor. The common factor accounts for the variance that's shared among the observed variables, while the unique factor accounts for the variance that's exclusive to each observed variable. The unique factor also includes an error term. Therefore, the leftover variance that is not explained by the common factor refers to the unique factor plus the error term. And this leftover variance includes both random error, which is inconsistencies that occur due to chance, and systematic error that the model did not account for. Now, systematic error could include method factors like similarities in item stems or negative wording, which might influence one's response. It could also stem from unassessed indicators, for instance, relevant variables or factors not included in your analysis. For instance, if we're evaluating therapy quality, there might be other important aspects like empathy, experience, or responsiveness that weren't assessed. In real-world data, this error variance might include variance that's shared with some, but not all other indicators. And this means that error variances of different indicators may not correlate with one another. Now, again, if you recall from the Venn diagram, this correlation is referred to as local dependence. And this implies an overlap of variance among variables that the model assumes to be independent. And to simplify this explanation a little bit, imagine you're trying to understand what makes a good therapist, and you think the key factors are good listening skills, diverse skill sets, and warmness. You collect data on these three qualities, but when you analyze it, you find that these factors don't fully explain why some therapists are better than others. The part you can't explain, or the leftover part, is the variance not explained by your factors. This leftover could be because of random things you can't predict, like a therapist having a bad day, or systematic things you didn't think to measure, like maybe therapists who are empathetic or very experienced are better. And sometimes this leftover part might be influenced by similar things in different qualities. For example, if a therapist's listening skills improve, their warmth might also improve. So the leftover part of the listening and warmth might move together. And that is what we call local dependence. So in short, when you're trying to explain something complex like therapist quality, it's hard to account for everything. And there's always going to be some part of the picture that you do not capture. And that is the leftover variance. Let's explore the concept of a two-factor EFA. So sometimes we may need multiple factors to account for indicator intercorrelations due to multiple item clusters. And I want you to think in terms of subscales on a survey. Here, we're going to describe this model as uncorrelated, meaning the factors are assumed to have no shared variance. In this case, we have the latent variables of verbal comprehension and working memory. Put differently, we have the factors of verbal comprehension and working memory. Each of these latent variables is presumed to have an impact on several observed variables, which are represented in the diagram by vocab, similarities, info, ... all the way to the indicator at the farthest right, LNS. What they represent is not important for the takeaway of this model in terms of what is LNS, what is DS. Those are just labels for the variables to fit in the graphical representation. Just remember that these are your indicators, and the E values represent the unique error for each indicator, which is including that variance not accounted for by the common factor. On a more technical level, in an EFA, remember that the goal is to identify a smaller number of factors that can explain the patterns of correlations among several observed variables. And when dealing with larger numbers of variables that appear to measure different constructs, like verbal comprehension and working memory, it may be necessary to use a two-factor or even more model. These constructs may have multiple item clusters, and this is similar to the subscales in the test that I was talking about relating to each latent variable. This assumes that the two latent variables are uncorrelated. In other words, each factor independently influences the indicators, and there's no overlap, like in the Venn diagram, or shared variance between the two factors. However, This assumption might not hold true in real-world scenarios. Often, the factors are correlated, and that implies that they share some variance, which is why we also have a second version of this model called the correlated model. And that's going to account for the correlation between verbal comprehension and working memory factors. In this model, not only does each factor influence the indicators, but there's also a relationship between the two factors themselves. That's represented in this diagram by the double-headed arrow, as you see here, between verbal comprehension and working memory. Imagine you're trying to understand a student's abilities in school. You might measure a lot of different skills like vocab, similarities, comprehension, arithmetic, and so on. However, it can get tricky to make sense of all these skills individually. So you decide to group them into two main categories, or factors. In the first scenario, you assume that these two categories are completely separate. That is, how a student performs in verbal comprehension doesn't impact how they perform in working memory. This is like saying that a student's ability to understand language has no effect on their ability to remember and use information. In this scenario, you think that these two categories might be connected. Seems logical that a student who is good at understanding language might also be good at remembering and using information. So you allow for the possibility that verbal comprehension and working memory can influence each other. This is why it's called the correlated model. In both these scenarios, you're trying to see how much of each skill, like vocabulary or comprehension, can be explained by these two categories. But remember, there will always be a part of each skill that these two categories cannot explain, and that is the E value, or again, the error term, which captures the unique parts of each skill that are not shared with others. We find these unique factors using an important concept in factor analysis called factor rotation. The goal of factor rotation is to simplify the interpretation of factors by redistributing the variance from the factors onto the observed variables in a manner that makes the structure of the factors more interpretable. Here, the observed variables are indicated as x1 through x6. Let's break this down. The table here shows the factor loadings of each observed variable, x1 through x6, on two factors, f1 and f2. Factor loadings can be thought of as correlations between your observed variables and the factors themselves. Higher absolute values indicate a stronger relationship. Initially, without any rotation, the factor loadings might not be easily interpretable because variables may load highly on several factors. The idea of rotation is to optimize the factor structure in a way that each variable strongly loads on one factor and has minimal loadings on the others. In this case, it seems to suggest that we use an orthogonal rotation, and this keeps the factors uncorrelated and rotates them to maximize the variance of the squared loadings within factors. More on this in the next slide. The graph here illustrates the results of this rotation. X1 through X3 are all in the first quadrant, and this suggests that they have positive loadings on both F1 and F2. But with stronger loadings on F2. On the other hand, X4 and X6 are in the fourth quadrant, indicating that we have positive loadings on F1 and negative loadings on F2. I want to give you a simplified explanation using a separate example. Imagine you're a clinical psychologist assessing a new patient. You're looking at different symptoms, their level of anxiety, their depression, their social withdrawal, aggression, hyperactivity, and impulsivity. But it's hard to figure out what matters most because all these symptoms are tangled up together, meaning it's hard to separate anxiety from depression, for instance. This is where factor rotation comes in. Factor rotation is like taking a step back and looking at your patient from a different angle. You're still looking at the same symptoms, but you're trying to line them up so you can understand them more clearly. F1 and F2 are like different perspectives on the patient, and X1 through X6 are the different symptoms. By rotating the factors, you're changing your perspective. You're trying to see the symptoms more clearly. So if the rotation works well, you might find that some symptoms like anxiety and depression line up together, and others, like aggression and impulsivity, line up separately. The table here is showing how much each symptom, X1 through X6, lines up with each clinician perspective, F1 and F2 after rotation. The graph is a visual representation of this. Symptoms, X1 through X3, whatever those may be, are more strongly correlated or related to F2 and less so to F1. And symptoms, X4 through X6, whatever those may be, are more strongly related to F1 and negatively related to F2. Let's talk technically about orthogonal rotation for a second. It assumes factors are uncorrelated, which means axes maintain a 90-degree angle during the rotation. This means that they are independent of one another by definition. And this independence is maintained by ensuring that the axes maintain a 90-degree angle during rotation. The goal of orthogonal rotation, as conceptually represented by the axes intercepting one factor, is to simplify the factor loadings. It aims to ensure that each variable, here x1 through x6, has a strong loading on one factor with the loading on the other factors as close to zero as possible. The goal is often referred to as achieving what's called simple structure. And the table here provides factor loadings of each variable on the two factors f1, f2 after orthogonal rotation. The result of the rotation can be seen clearly. x1, x2, and x3 have near zero loadings on f1 and strong loadings on f2, while x4, x5, and x6 have strong loadings on f1 and near zero loadings on f2. The graph provides a visual representation of these factor loadings. After the rotation, x1, x2, and x3 are close to the vertical axis, which is f2, and x4, x5, and x6 are close to the horizontal axis, which is represented as f1. This suggests that these variables load strongly on these respective factors and very weakly on the other factors. And let's go back to our clinical psychology scenario as a more simplified explanation. So you've been trying to find the best perspective to clearly understand your patient's symptoms. The aim is to line up each symptom so that it strongly aligns with one factor and minimally with the others. Now, when you observe your patient, some symptoms, x1 through x3, align very well with one factor, f2, while other symptoms, x4 through x6, line up with a different factor, f1. And the symptoms that align with f1 don't overlap with f2 and vice versa. This is what the table and graph are showing. It's basically showing how well each symptom aligns with each factor after you've found the best rotation. In other words, orthogonal rotation is like finding the best perspective to clearly see your patient's symptoms. In many research scenarios, factors are typically correlated. This means that they share some degree of variance, meaning they might affect the same observed variables to some extent. And in this particular table and graph shows where factor loadings of each observed variable, the x's on two factors, the f's, in a situation where these factors actually might be correlated. So unlike the previous orthogonal rotation, where loadings on one factor were close to zero, here variables load on both factors. So for instance, x1 loads on both f1 and f2, suggesting that it's influenced by both factors. The graph provides a visual representation of these factor loadings. It shows that x1 through x3 are clustered in the first quadrant, indicating they have positive loadings on both f1 and f2, and x4 through x6 are clustered in the fourth quadrant, indicating they have positive loadings on f1 and negative on f2. Now, let's go back once again to our simplified explanation. Imagine the factors are different aspects that contribute to the complexity of a patient's condition. In reality, these factors, such as levels of anxiety and social withdrawal, are not completely independent. Someone who is socially withdrawn might also exhibit high levels of anxiety, and these aspects might influence other symptoms. And in this slide, it's showing that when you look at a patient's condition from a certain perspective, some symptoms like x1 through x3 seem to be influenced by both levels of anxiety and social withdrawal, the Fs. Other symptoms like x4 through x6 are also influenced by both factors, but in a different way. They increase with someone's level of anxiety, F1, but decrease with social withdrawal, F2. The graph is like a map of the patient's condition. It shows that some symptoms x1 through x3 go together and are in one area of the symptom spectrum, which is what we see in the first quadrant. The other symptoms, x4 through x6, are clustered together in a different area, the fourth quadrant. But all of these symptoms are affected to some extent by both anxiety levels and social withdrawal. So what does orthogonal rotation assume? Well, if you remember, it's that the factors are uncorrelated. This means that these latent variables have no shared variance. This means that if you were to use orthogonal rotation on the correlated factors from the previous slide, would lead to difficulties in achieving what is known as that simple structure I was talking about. Because the simple structure is a pattern of factor loadings where each observed variable, like x1, x2, has a high loading on one factor and a near zero loading on all the other factors. And this pattern simplifies the interpretation of the factors because each observed variable is primarily associated with one factor. In the case where factors are correlated, this is where we would use an oblique rotation instead. Again, in this graph, we're seeing the byproduct of using an orthogonal rotation on correlated factors. The idea is that they should line up on one of the axes, and our x4 through x6 is not quite there yet, which is why in the case where factors are correlated, oblique rotation is much more suitable. Unlike orthogonal rotation, oblique rotation allows for correlations between the factors. Here, the factor loadings resulting from an oblique rotation with each observed variable predominantly load now on one factor. I want you to relate the concepts of orthogonal and oblique rotation to categories for assessing a patient's psychological condition. Orthogonal rotation is like trying to categorize symptoms strictly by either anxiety or social withdrawal, and that's it. This system assumes that the anxiety category and social withdrawal category are unrelated, like symptoms of anxiety don't correlate with symptoms of social withdrawal. However, this is not always true because a patient may be exhibiting anxiety because they are also showing significant signs of social withdrawal. So in reality, these categories are somewhat related. And using a strict anxiety or social withdrawal system, the orthogonal rotation, could make it hard to interpret the patient's condition in a way that makes sense. In other words, achieving the simple structure. Oblique rotation is like acknowledging that the anxiety category can relate to social withdrawal. And using this information, you would interpret the patient's symptoms. This could make it easier to understand the patient's condition. Like most of this patient's symptoms are related to anxiety, so we'll put them all in the anxiety category. And this table of numbers that you see here is just showing that each symptom primarily fits in one category. You've seen this diagram before, and let me make it more clear. As before, we were just talking about it as an uncorrelated model. Well, sometimes we may need multiple factors to account for indicator intercorrelations due to multiple item clusters. Remember thinking in terms of the subscales? Well, here, these factors are uncorrelated, and each arrow in the diagram represents a factor loading, which is, again, a measure of how much the observed variable, like vocab, is influenced by the latent factor. The E represents the unique error associated with each variable, which is a variance in the observed variable not explained by the factors. Now, orthogonal rotation methods like Varimax are more straightforward and yield factors that are easier to interpret. These methods are useful when the constructs you're measuring are theoretically unrelated, and for certain statistical procedures like variance decomposition. On the other hand, you've also seen this diagram. This is in contrast to the orthogonal rotation. Oblique rotation allows for these factors to be correlated, and this means that the underlying constructs can share some variance. This rotation is used when factors are believed to be related in some way. And the double arrow line here from verbal comprehension to working memory represents this allowed correlation. And each observed variable can now be influenced by both factors, with the magnitude of influence still represented by the factor loadings, which are the arrows from the factors to the variables. Oblique rotation methods such as Promax or direct Oblique can yield more accurate and possibly more insightful results when the constructs being measured are related. This technique is typically chosen when there are theoretical or empirical reasons to believe that the factors might be related. If the variables in your study have low correlations, it suggests that the factors are unrelated, and an orthogonal rotation may be appropriate. Orthogonal rotations tend to yield simpler and more parsimonious explanations of the data because they aim to maximize the independence of the factors. On the other hand, oblique rotation allows for correlations between the factors. And this type of rotation produces factor solutions where the factors can be correlated or interrelated. And in real world scenarios, again, variables and constructs are often related to some extent. If there is a theoretical basis or prior knowledge suggesting that the factors are correlated, or if the variables themselves are highly correlated, an oblique rotation is going to be more suitable. Oblique rotations are beneficial when factors are expected to have a shared variance, or when there's a possibility of a higher order factor structure. It's important to note that the choice of rotation method does not change the fundamental factor structure underlying the data. It only aids in the interpretation of the factors by providing a more meaningful and interpretable solution. And ultimately, the decision should be based on the theoretical understanding of the factors and the research goals. The chosen rotation method should align with your theoretical expectations, and it should also make sense in the context of your study. Exploratory factor analysis serves two primary goals: identifying latent variables that give rise to the observed variables. And again, I can't stress this enough. Latent variables are the hidden or unobserved variables that cannot be measured directly, but they are inferred from observed variables. And the second primary goal of EFA is to determine the number of common factors required to explain the interrelationships among observed variables, also known as the dimensionality of the measure. A factor in EFA is that latent variable that's thought to cause the patterns of correlation among your indicators. And determining the number of factors is one of the most critical and challenging steps in factor analysis. It's a balance of mathematical rigidity and your theoretical justification. And this is because EFA doesn't provide a strict rule for the number of factors. It just requires some theoretical underpinning or justification. To simplify this, let's say you're trying to understand the qualities that make a therapy modality popular. The observed variables might be elements like length of treatment, pace of appointments, the therapist's style, etc. The latent variables or factors could be treatment complexity or therapist influence. EFA aims to identify such latent factors and find out how many such factors can explain the relationships among our observed variables. And how do we do this? Well, this leads me to an important concept called eigenvalues, and they help us determine the number of factors in EFA. And I want you to understand first, what is an eigenvalue? So recall in EFA, we generally work with a correlation matrix where the variances are all set to 1 across the observed indicators. The sum of these variances equals the number of indicators, which in turn equals the number of eigenvalues, and the sum of the eigenvalues. So in other words, if we have 7 observed variables, the sum of all the eigenvalues should also equal 7. An eigenvalue represents the amount of variance in the observed variables that a factor accounts for. A larger eigenvalue indicates that a significant part of the variability in the set of observed variables can be explained by that factor. The number of large eigenvalues equals the number of common factors. In simpler terms, if our therapy modality popularity study resulted in an eigenvalue of 2, or the quote treatment complexity factor, if you recall what I was talking about in the previous slide, it suggests that this factor would explain a significant amount of variation in treatment lengths or the appointment tempo, etc. Now, for those of you familiar with multiple regression analysis, this is akin to the concept of R squared, which represents the proportion of variance in the dependent variable that can be predicted from the independent variable or variables. Eigenvalues and R squared are analogous in that they both quantify the amount of variance explained by a set of variables or factors. And there's several rules of thumb to guide the decision about the number of factors to retain involving eigenvalues. The first one is the Kaiser-Guttman rule, and this rule suggests that retaining all factors with eigenvalues greater than 1 would mean that any factor that explains more variance than a single observed variable is worth keeping. However, this rule is often criticized for overestimating estimating the number of factors. Hence, we call this a lousy rule. We also have the Scree test. The Scree test involves plotting the eigenvalues in descending order and identifying the point where the slope of the curve becomes less steep, in which this looks kind of like an elbow. Factors to the left of this point or left of this elbow would be the ones that are retained. While this is more visual and subjective, this method actually tends to be more accurate than the Kaiser-Guttman rule. We also have parallel analysis. Now, this method involves comparing the observed eigenvalues with those obtained from randomly generated data. This is kind of similar to bootstrapping in terms of how we're extracting this data and comparing. Factors are retained if the observed eigenvalues exceed the corresponding eigenvalue from the random data. And parallel analysis is often considered more accurate as it corrects for sampling error and the tendency for EFA to naturally extract too many factors. In addition to looking at the number of factors based on the eigenvalues, Kaiser-Guttman rule, and the Scree test, and also parallel analysis, we need to look at model fit. And model fit refers to how well a statistical model represents the data that it's designed to approximate. There are several indices and tests that can be used to assess model fit in factor analysis. And these include the chi-square test and other fit indices like CFI, TLI, RMSEA, SRMR, and information criterion like the AIC and BIC. These measures help assess whether our model is a good fit for our data and whether adding more factors improves the fit. I will go over these fit indices in a few slides. So if we're determining the number of factors using the Kaiser-Guttman rule, the rule states that we should retain all factors with eigenvalues that are greater than 1. And the rationale behind this rule is that any factor that explains more variance than a single observed variable is worth keeping. According to the Kaiser-Guttman rule, we should retain the first two factors here because their eigenvalues are greater than 1. Notice at factor 3, it is less than 1. Therefore, we know, according to the Kaiser-Guttman rule, that our factor solution is 2. But a significant problem with the Kaiser-Guttman rule is that it can lead to over extraction, meaning we might end up with more factors than we theoretically should have. These extra factors are often referred to as nuisance factors, which may not contribute much meaningful information and can complicate the interpretation of our results. Therefore, while this rule may be a helpful starting point, it should not be solely relied upon. Looking at the next rule of thumb, which is the Scree test. Again, that's used to determine the number of factors to retain. And the Scree test involves plotting these eigenvalues in descending order and looking for the point where the curve slope dramatically changes, or we call it the elbow, or you could think of it as a hockey stick. The number of factors to retain is typically those left of this elbow. Again, taking this example of eigenvalues, if we plot these values in descending order, we look for the point where the slope of the curve shifts sharply. This elbow indicates we should stop retaining factors. So problem with this is I could almost make two cases for where the elbow is. You could look at the elbow here, or larger picture, you could look at it here. This is one of those cases where the Scree test is highly subjective. Now, if we were to use this solution, we would see that the elbow point is about right here at 2. And according to this rule, it's at the point where the curve slope changes, and it's supposed to be to the left of this elbow. So that means we have a 1-factor solution here, potentially a 2. We'll call that maybe. However, if we look at it from a elbow standpoint here, notice it's at 4. So we know this would not be a 4-factor solution, but this could be a 3-factor solution. Remember, the elbow is not always clearly identifiable, and this will lead to disagreements regarding the number of factors to retain, such as this plot. This is the same plot shown in R. Notice the point of 2, point of 3, point of 4 again. If we designate this as the elbow, we have a 1-factor solution. If we designate this as the elbow, we have a 3-factor solution. Now, parallel analysis. The idea here is that we want more than the simulated data. So the number of factors is determined by the number of eigenvalues, which is the white line here, that are above the values obtained from the simulation, which is our red line. And in parallel analysis, we're going to compare our eigenvalues from our actual data to this randomly generated data. So in this case, the first 2 factors from our actual data have eigenvalues greater than the corresponding eigenvalues from the simulated data. And this indicates that we should retain At least one factor. Here, if we were being really picky, this red line to me shows a little bit of white underneath it. And I would say that this would be a one factor solution. Depending on how stringent you want to be, this could be a potential two factor solution. But I would be weary of this. And this goes back to, if you look at the table, this is greater than the value in the parallel analysis, but this does not. So therefore, this would be a one factor solution. The chi-square test is a statistical tool that helps us understand how well our proposed model, such as a one factor, two factor, or three factor model, fits the data we've collected. The null hypothesis here is that there's an assumption that there's no significant difference between the relationships our model predicts and the relationships we actually see in the data. And here's how it works. We have the chi-square test for model fit, and this checks the overall fit of the model. If the p-value, which measures our statistical significance, is low, this indicates that our model does not do a great job of representing the actual data. In technical terms, we say there's a significant misfit. Then we have the chi-square difference test. This is used when we want to compare two different models. It tests whether adding another factor, for instance, moving from a one-factor model to a two-factor model, significantly improves how well the model fits the data. Now, let's take a look at this example. The one-factor model has a p-value of less than 0.001, which is significantly less than 0.05, which is a common threshold for statistical significance, which suggests also that the one-factor model does not represent the data very well. It's a poor fit. The p-value for the two-factor model is 0.0861, which is greater than 0.05, and suggests that the model fits the data better than the one-factor model. In other words, it's a better representation of the relationships in the data. Then, when we compare the one-factor model to the two-factor model using the chi-square difference test, the p-value is less than 0.001 again, and this indicates that the two-factor model is a significant improvement over the one-factor model. However, when we compare the two-factor model to the three-factor model, the p-value is 0.0771, greater than 0.05, suggesting that adding a third factor doesn't significantly improve the fit of the model. So overall, the two-factor model appears to be the best choice thus far. It fits the data better than the one-factor model, and adding a third factor doesn't provide a significant improvement. I want to note that the chi-square test is highly sensitive to sample size, and in large sample sizes, even trivial deviations from the model can produce a significant chi-square, indicating a poor fit, even if the model is practically acceptable. There are also other ways to evaluate the quality of a factor model. In addition to the chi-square, there are several other indices that help us understand how well our model fits our data. And we're going to focus on the CFI, which is the comparative fit index, the Tucker-Lewis index, commonly referred to as TLI, and the root mean square error of approximation, most notably found in the literature as RMSEA. I want to start with the CFI and TLI, and these are what we call incremental fit indices. And what does that mean? Well, they're basically comparing our model, the one we've developed based on our data and our theory, with a very basic null model. And the null model says that there is no relationship between our variables. It's considered the worst case scenario. So the CFI and TLI are giving us a score to show how much better our model is compared to this worst case scenario. They both range from 0 to 1. If they're closer to 1, that's good news. It means our model fits the data much better than the null model. We're looking for a value ideally over 0.95, but anything over 0.9 is generally acceptable. However, there's a little caveat here. If our null model is not too bad to begin with, and that's determined by a measure, the RMSEA, which we're going to talk about next, these indices might not be very informative. It's kind of like being proud of winning a race when the other competitors weren't very fast. But as long as our null model is truly a worst case scenario, the CFI and TLI are pretty useful. These indices are less sensitive to sample size than the chi-square, but they still may over-reject the true population models when sample size is small. And I want to dive a bit deeper into the RMSEA and the standardized root mean square residual, the SRMR. The RMSEA is what we call an absolute fit index. You can also consider it like a parsimony adjusted index, meaning that it also considers model complexity. Instead of comparing our model to another model, the RMSEA considers the discrepancy, or the error, between our observed data and the hypothetical perfect data that we would expect if our model was the true model. It's trying to measure how well our proposed model represents the data we actually collected. And basically, it's telling us how much our model misses by. Specifically, it's calculating an average of the discrepancies, or the differences, between the correlations our model predicts and the correlations we actually observe in the data. And think about it this way. Let's say we have a model that predicts there will be a strong positive correlation between two variables, like hours spent studying and test scores. But when we collect our data, we find that the correlation isn't as strong as our model predicted. This difference is a discrepancy, and the RMSEA calculates an average of all these discrepancies across our model. Now, the lower the RMSEA, the better. If it's low, it means our model's predictions are quite close to our actual observations. If the RMSEA is less than 0.06, we generally consider this to be a good fit, meaning our model does a pretty good job of representing the data. If you want to be more conservative and be more precise, you should use less than 0.05 as the rule. It's one of the most commonly reported indices, as it has good properties and is less sensitive to sample size than the chi-square. But then we have the SRMR, the standardized root mean square residual, and it's another absolute fit index. And like the RMSEA, it's comparing our model's predictions to our actual observations. But instead of looking at discrepancies in the correlations, it's focused on the square root of the average squared discrepancies between observed and predicted correlations. This brings the root mean square part of its name to life. So if our model predicts a strong correlation between two variables, but in our data, we observe a weaker correlation, the SRMR considers this a residual. And the SRMR then averages all of these residuals across our model to provide an overall measure of model fit. Again, a lower SRMR is better. It indicates that our model's predictions are very close to our actual observations. If the SRMR is less than 0.08, we typically consider this to be a good fit. Both of these indices are helping us answer the question, how well does our model represent the actual patterns we see in our data? They just do it in slightly different ways, which is why it's often a good idea to look at both when assessing model fit. And like regression, exploratory factor analysis sometimes needs you to create multiple models as you try to find the best way to explain your data. You need a way to compare these models and decide which one is best. And that's where the Akaike information criterion, the AIC, and the Bayesian information criterion, the BIC, come in. The AIC and BIC are measures used to assess model fit, but with a particular focus on model comparison and complexity. They're particularly useful when you want to compare multiple models and need a criterion to determine which model provides the best balance between fit and complexity. The AIC and BIC both take into account the goodness of fit of the model and the number of parameters used, which is the complexity of the model. In general, a good model is one that provides a good fit to the data while using as few parameters as possible. This reflects the principle of parsimony. AIC is generally more liberal and may suggest a more complex model. It's often used when the goal is to predict future observations, and the true model is considered unknowable. If you're more interested in prediction or have less certainty about your theoretical model, you might prioritize AIC. BIC, on the other hand, penalizes complexity more heavily and therefore leans toward more parsimonious models, especially as sample size increases. If you have a strong theoretical model and are interested in inference about the model, you might give more weight to the BIC. They're kind of like scores in a game. The model with the lowest score, AIC or BIC, in this case, would be the winner. But what makes these tools really useful is that they don't just look at how well the model fits the data, they also take into account how complex the model is. And why does complexity matter? Well, it's pretty easy to make a model that fits your data perfectly just by making it really complicated. But that model might not be very useful because it's so specific to your data that it might not work well with other similar data sets. This is often referred to as overfitting. AIC and BIC help us avoid overfitting by penalizing models that are too complex. This way, we encourage parsimonious models, which is, again, just a way to say models do a good job with as few factors as possible. As a general rule, lower AIC or BIC values indicate a better model, but how much lower? Well, a good rule of thumb is a change of more than 10 in either AIC or BIC is considered decisive. And this is based, again, on a rule of thumb suggested by Cass and Rafferty in 1995, and it gives us a practical way to decide between models. So in simple terms, AIC and BIC are the referees in a game between different models. They score each model not just on how well it fits the data, but also how simple and useful it is. The model with the lowest score would be the winner in this case. So results thus far. Our Kaiser-Guttman said 2 factors. Our Scree test said 1, potentially 3. The parallel analysis said 1, almost 2. Chi-square said 2, almost 3. So this leads me to think about theory and interpretability. And despite the wealth of statistical measures and guidelines that are available for determining the number of factors, factor analysis is not solely a mechanical or mathematical task. The interpretability of the factors and their consistency with theoretical expectations are equally, if not more, significant. Ultimately, the factors derived should resonate with the data's context and the research question at hand. For example, the factors recognized in assessment of a patient's psychological symptoms should be interpretable as aspects of the psychological conditions or experiences. Similarly, the number of factors retained should correspond with the theoretical expectations or prior research. And this should offer a comprehensive and meaningful understanding of your data. So recall that EFA uses the correlation matrix of various indicators to estimate a model. And these indicators can be anything. They can also be, another example we haven't used yet is IQ test results or answers to a personality quiz. Now, the correlations or the relationships between these indicators are standardized, which means that the values are adjusted so that they can be compared on the same scale. For example, in a study of intelligence, these indicators could be different types of IQ tests. It makes sense then that any factors or underlying structures that we find in the data should align with different aspects of intelligence as defined by previous research and theories. Now, factor loadings are a key part of understanding the results of EFA. Remember, they're going to represent the strength and direction of the relationship between each observed variable, which are the indicators, and the underlying factors. A positive loading means that the factor score increases, the observed variable will also tend to increase. Whereas a negative loading means that as the factor score increases, the observed variable decreases. These factor loadings range from -1 to 1, and they are going to be very critical in interpreting the factors. And a high absolute loading value, whether it's positive or negative, shows that the factor has a strong influence on that variable. Conversely, a low loading suggests a weak influence. So I want you to really think of this in terms of absolute value, which is distance from 0. So -1 and 1 being equal because they both are 1 unit away from 0. And loadings can be considered strong or significant based on certain thresholds, which are often set by researchers. And generally, an absolute loading of 0.3 or more is considered significant. And this would imply that the factor explains at least 9% of the variance or the variability in the observed variable. And that's because 0.3 times 0.3 would be 0.09. Move the decimal over twice and you get 9%. Now, a loading of 0.5 or more is considered strong as the factor explains at least 25% of the variance in the observed variable. And again, that's multiplying 0.5 times 0.5, which gives you 0.25. Move the decimal over twice, you get 25% of the variance. Now, remember, these thresholds are just guidelines and might be adjusted based on the specific requirements of the study or the researcher's discretion. And one important point to remember is that the factor loadings are standardized. This means that regardless of the original scale of the variables, the loadings can be compared directly across variables and across factors. So again, how many factors? Well, let's look at an example of a 1 factor, a 2 factor, and a 3 factor solution. What what we want to see. We want to see that 3+ indicators load strongly on each factor, and we want to see a simple structure, meaning each indicator loads strongly onto one factor. Now consider the example where we conducted a factor analysis to look at the structure of an IQ test. In a single factor model, some tests seem to have high loadings, meaning they're strongly related to each other. These are very strong loadings. Others, like TOPF, have a very weak loading, which indicates a weak relationship with the factor. In a two-factor model, the factors may represent different aspects of intelligence. So for instance, the first factor may represent verbal IQ. So this would be verbal IQ. And that's strongly linked with tests like vocab, similarity, information, and potentially, this matrix variable. The second factor, on the other hand, might represent perceptual reasoning IQ. So this could be perceptual reasoning IQ. And this would be connected to tests like visual puzzles or blocks. Notice the loadings here. Now, while factor analysis is powerful, it requires careful interpretation and understanding of several concepts. We need to think of cross loadings, and that occurs when a variable has high loadings on more than one factor, suggesting it's not unique to one factor, which could complicate interpretation because a simple structure is desirable. And that's where each variable loads strongly onto one factor and weakly onto others, because this simplifies the interpretation of factors. And here, where do we see this happening? Right here. Notice for similarity, it loads very strongly on factor 1, but it also gives an adequate loading on factor 2. So this might be a case of using a 3-factor model, but beware of nuisance or method factors because they may not emerge from a shared content among the variables, but from commonalities in the data collection method. And remember that each factor should ideally have multiple strong indicators, and again, 3 or more, ideally, to ensure that they're reliable and stable. And factors with few indicators may not be reproducible or reliable. And when we move to the 3-factor solution, notice the only variable loading onto factor 3 is the matrix variable. All other loadings do not make the threshold. And this already goes against the number of indicators you want to see. We want to see 3+. This doesn't even reach the threshold of 2, which would still be pushing it. So therefore, a 3-factor solution is not very good. But then that leads me to, what do we still do with this similarity? Well, the way I see it here is, if I'm going to make a judgment call as a researcher, I'm noticing that it loads very, very strongly on this first factor. It's also loading very, very strongly when it's a 1-factor solution. But then when we extend it to a 3-factor solution, it still loads very strongly. In fact, it increases and it decreases with the second factor from 0.30 to 0.20. Therefore, I would make a judgment call and say that this is a 2-factor solution, and this item is going to load with factor 2. So at the end of the day, we're going to say that factor 2 is going to comprise of these 3 indicators. Factor 1 is going to have these 3 indicators. None of these are high loadings from this one item of TOPF. Therefore, we're probably going to toss out the TOPF item. This will be gone. This will be our first cluster, our second cluster. Factor 1, factor 2. Home stretch. And this is a very higher level concept that I think is also very important though, which is the random intercept exploratory factor analysis. This is known as a multi-level exploratory factor analysis, and it's used when analyzing data with a hierarchical structure, like patients within different clinics or offenders housed in different prisons. I have 2 scenarios to illustrate this. Let's consider a clinical psychology scenario first. Suppose we're researching the impact of various therapy sessions on stress management among patients from different clinics. Due to a variety of factors ranging from environmental conditions to patient demographics or the specific therapeutic approach used, stress levels can actually fluctuate significantly between clinics. And a patient's stress score is not just an individual measure, but it's also shaped by the overall stress environment of their specific clinic. In this context, the random intercept EFA model acknowledges the dual nature of each patient's stress score because it considers both shared factors, which represent common patterns of stress levels across all clinics, and individual factors, or the random intercepts, representing the mean stress level unique to each clinic. However, a clinic's high average stress level might cause its patients to score higher on the stress scale, not necessarily because of their individual stress, but due to the overall stress environment of the clinic. And this can mask the common patterns we're trying to uncover, as it distorts the relationships among individual stress scores. Here, the random intercept EFA proves invaluable because it introduces a random intercept factor that accounts for these clinic level differences. By centering each patient's stress score around their specific clinic's average stress score, which is a process known as within clinic mean centering, the random intercept isolates the clinic level variance. And this allows for a more precise estimation of the common patterns across all clinics and patients, and thus enhances our understanding of stress management effectiveness. This technique, though, operates under orthogonal rotation, meaning we assume that the random intercept factor, which captures differences in overall clinic stress levels, and the shared factors representing common stress patterns across clinics are unrelated. Here's another example. Let's say in forensic psych, we want to analyze aggressiveness among offenders in different prison systems. And just like the clinical scenario, the aggression level can vary significantly from one prison to another due to factors like overcrowding, living conditions, or even just the effectiveness of the rehabilitation program. In this context, the random intercept EFA model sees each offender's aggression score as a blend of their personal tendencies and the overall aggression level of their specific prison. The underlying latent factor model takes into account both shared factors, so common patterns of aggression across all prisons, and individual factors, or the random intercepts, which is the average aggression level of each prison. Here, too, an offender might score high on an aggression scale, but not necessarily due to their inherent aggression, but due to the overall aggressive environment of their prison. Such prison level differences can distort the relationships among individual aggression scores and mask the common patterns of interest. With this new random intercept factor that we're introducing in the random intercept EFA, we hope to separate out these prison level differences by centering each offender's aggression score around their specific prison's average aggression score, or within prison mean centering. It isolates the prison level variance, and this allows a cleaner estimation of the common patterns or factors, providing a more accurate picture of the aggressiveness across different prison systems. Just like in the clinical example, we assume orthogonal rotation here because the random intercept factor, which is capturing differences in overall prison aggression levels, is considered unrelated to the shared factors, which is the representation of common aggression patterns across prisons and offenders alike. The primary reason that random intercept EFA doesn't typically allow for correlated factors is that the random intercept factor is designed to account for a specific type of variation, the individual level differences in overall levels. It's meant to remove these individual level or group level differences to reveal the common underlying factors. And if the factors were allowed to correlate, then the random intercept factor might also correlate with the common factors. And this makes it hard to separate the individual level differences from the common variance. This correlation would risk confounding the influence of the individual or group level differences and the common factors, potentially leading to misleading results. Now, this assumption further enhances the robustness and accuracy of this particular analysis. As a quick review, both EFA and PCA aim to simplify a larger set of variables. They differ in their approach, though. EFA seeks to uncover latent factors influencing the variables, while PCA focuses on summarizing data through creating components without any assumed theoretical relationship. EFA aims to uncover the underlying structure of the data and identify the latent factors influencing observed variables. And in contrast, PCA is more about data reduction and summarization, not relying on a theoretical relationship between the variables. So what is it that we're analyzing in EFA? Well, we're looking at a shared variance or commonalities among our variables, seeking to explain correlations through the identification of latent factors. Now, why do we rotate in factor analysis? Rotation be it orthogonal or oblique, helps us make the output more interpretable, and that clarifies the relationships between observed variables and factors. Now, when you decide the number of factors in EFA, we use the Kaiser-Guttman rule, the Scree plot, the parallel analysis, chi-square test, and theoretical considerations. And then what about model fit? Well, it's about how well our chosen model represents the actual data. The better the fit, the more reliable the analysis. And the measures we use to assess model fit are the chi-square tests, the root mean square error of approximation, known as the RMSEA, the comparative fit index, the CFI, and the Tucker-Lewis index, the TLI. They're all measures we use to understand how well our model fits the data. In terms of how the chi-square test works for model fit, it compares observed data with what the model predicts, and a significant p-value from this test indicates that the model doesn't fit the data very well. And what about RMSEA? Well, it evaluates the discrepancy between the observed covariance and the model covariance per degree of freedom. We generally want an RMSEA of 0.06 or less for good model fit, but it's particularly better if we use 0.05 or less. Now, to move on to the CFI and TLI, both of these indices compared to our specified model with a null model, assuming no relationships among variables. Values close to 0.95 or above indicate a good fit. Remember that fit indices help us evaluate our model, but no single index tells the whole story. And the key takeaway is that it's often most informative to use a combination of fit measures when assessing your model. Each fit index has different strengths and limitations, and together they can provide a comprehensive picture of how well your model fits the data. Always consider the specific context of your analysis, and remember that fit indices are just tools to guide judgment, not replace it. Thank you very much for staying through the entire video and learning more about exploratory factor analysis. If you have any questions, please message me and I'd be happy to answer. And next, we will be discussing confirmatory factor analysis.